my great pleasure being here to you today and talking about my work. In my talk, I basically have 3 different parts that show different perspectives on my research on visual analytics. In the first part, I really talk about how to design big visual analytic systems that really can facilitate the analysis of large and complex data sets. In the second part of my talk, I address how can we actually evaluate those systems to make sure that they're any useful, and how can we measure and compare them to make clear or to put a number on the usefulness. And finally, at the end of my talk, I would like to give an example of human-centered research showing how a design study can be really used to understand the needs of a user community in order to design new visual analytic tools. At the beginning, I have a very brief introduction to visual analytics and also to investigative analysis. So we are all very familiar with the big data challenge across all domains. There's lots of data, and it's very challenging to analyze it and to turn data into insight. And visualization is just one approach how we can turn data into insight. And I believe that visualization is a good tool to do that because the human vision is really our highest bandwidth sense, and it works fast and parallel. We as humans are really good at recognizing patterns, and our human vision system works pretty attentively. And I want to give a brief example on how that's related to textual data. So on this display, how many 3s do you see?
None.
At least one. One. Or, wait.
3. 4. 5.
Count the one in the title.
On this display, how many 3s do you see?
5.
5.
So that's basically called pre-attentive processing, where our visual system is very good in recognizing a pattern. And that's really interesting to put it into context of unstructured data such as text, because if you have just a string of characters, you really have to process this string in a sequential way. You have to go through it one by one. It's very slow, and it's very difficult to find what you're looking for. However, if we can apply computational techniques to automatically extract information that's relevant, and then use visualization to really highlight this information, we can make it much more easy to really identify and show you the data that you're interested in. And this really leads to the area of visual analytics, where we now combine both a visualization approach and also automated analyses that are tightly integrated with visualization to facilitate the data analysis process. And the idea is that it's not a pipeline anymore, as we used to work with in information visualization a while back, where we basically start off with data, then we transform it, and we find mappings to map the data onto visual representations, and then we do the interactive analysis. In visual analytics, we are much more interested in having this combined analysis that applies data mining or other automatic approaches and integrates them tightly with visual representations so that the analyst can choose which one would be most beneficial to do the task at hand. And my area of research is really broadly in the domain of investigative analysis. And there are lots of sub-areas. For example, I was working with, originally at Georgia Tech, with the intelligence domain, because we had funding from DHS to really develop tools that help intelligence analysts to go through a large amount of case reports to find connections between people, places, organizations, and so on. But of course, there's also another really interesting area, which is science. In science, we also have a huge amount of existing knowledge, and we always have to put our new discoveries or outcomes from experiment into the context of the existing knowledge. And that's getting increasingly difficult because there's so much existing knowledge. And especially in the biomedical domain, where the borders between disciplines are breaking down, it's getting much more challenging to keep track of what's already known and how does it relate to my experiment. And therefore, I've developed a tool that really addresses this information problem that's tailored to textual information. And it's broadly applicable to lots of domains, including intelligence, science, reporters, lawyers, and so on. And I support 2 different tasks. One is to find information in a large set of documents, and the second is to make sense of it, to put those nuggets, those pieces of information together to tell a more coherent story. And there are two different types of scenarios that are often used in the investigation domain. One is called a targeted analysis scenario. In intelligence analysis, for example, there was some intel on a bad guy, and I really want to figure out what is his social network, where has he been, what is the plan? In science, this could be an outcome of an experiment. For example, in biomedical research, if I have a microarray experiment, I know that a number of genes have been over or underexpressed. So that's my target. I really now would like to understand what does it mean and how does it relate to the existing knowledge. A second type of scenario is more an open-ended strategic analysis scenario. Examples for that would be in intelligence analysis, somebody is assigned to learn as much as possible about Libya without a specific question. But then later on, there will be the question about what do you expect is going to happen the next week based on what you know? And again, in science, it would be more, if you're learning about a new area, you would like to publish a paper in an area you're not familiar with. What's out there? How does that research relate to your research? So it's much more an open-ended question. And both scenarios have something in common. They both often follow an hourglass shape analysis process, where at the top, you start with a lot of data and you really don't know what to look at. And then you either apply interactive or computational techniques to find a point of interest. And then you really narrow down and you're trying to understand as much as possible about this specific data point. Once you're done with that, you really would like to relate this insight again into the bigger picture, and you widen your analysis process and you bring in, again, other data points that are really related to your insight that you just found. And then you basically continue this kind of loop of widening and narrow down to really find a bigger story and create a picture of your analysis result. And there are different types of metaphors that are used for that process. Lots of people compare it to looking for the needle in the haystack. But I think that's a really bad analogy because it's really just a search. You have a unique object that you want to find, it's not very difficult. Another analogy is that looking for a needle in a stack of needles. That's a little bit more complicated, but it's still just a search, and it doesn't really represent the idea of having an investigation. I like to use a different metaphor. I like to use the metaphor of a jigsaw puzzle. But it's not just one puzzle. So just imagine you have 10 different jigsaw puzzles, and you take all of them and put them into a big bucket. Then you take 10% of the pieces and just throw them out, because you never have all the data. There's always uncertainty. There's always things that you don't know. And then the question is, basically put those pieces again together and tell me what are the two most interesting pictures you see on these puzzles. So it's a much more complicated process, and it's not about finding specific information, but it's about understanding information in context, finding connections, putting pieces together. And to support this type of analysis, I've built a system, and I call it Jigsaw, basically using this analogy to make clear that it's not about a search, but it's really about finding knowledge and telling a bigger story that's coherent. And the system is really tailored to unstructured data, especially textual document collections. And I use multiple visualization views that are connected and that show connections between documents and entities within those documents. And the entities are always specific for a domain. In biology, I'm really interested in proteins, genes, pathways, Go annotations, and their connections. In the intelligence domain, I'm really more interested in people, places, organizations, and so on. And the views are highly interactive and also coordinated, meaning that if I'm interacting with one view, those interactions are reflected in other views to have a consistent information display. And one really important point is to automatically identify entities of interest in those document collections. And that's really not my main research expertise, and therefore I collaborate with lots of researchers in different domains that have the expertise to do that, and I integrate different tools that can automatically identify entities of interest. So in the Jigsaw tool, I've integrated the gate, the link pipe, the open Calais, and the Illinois named entity tagger. And additionally, I also implemented simple rule-based and dictionary-based approaches to allow users to identify entities in domains where these automatic tools don't exist. And then once we have these entities, it's all about connections. And I use a very, very simple definition of connections. I just call two entities connected if they co-occur in a document. So there's no semantic meaning associated with the connection. And of course, this can create kind of false positives. If a document states that John has never met Peter before, in my system, they are still connected because they co-occur in the document. However, it turns out that even this definition is very basic and very simple. It is still very useful and very powerful in practice. One reason for that is it's very easy to understand. Every analyst will immediately understand what it means that entities are connected. And in the end, the system is also not about replacing the reading of documents, but it's really more like an interactive visual index that helps an analyst to quickly find the documents that are important to read. And then at the end, when the analyst is reading the document, the semantic of the connection becomes clear, and these false positives can be easily identified. In addition to connectivity, I also put a weight on connections, or strengths. And I basically define that connections are more strongly connected if they co-occur in multiple documents. If they just co-occur in one, they're not as strongly connected. Additionally, to entity identification, I also have implemented a number of computational text analyses that can really help the analytical process. So I use document summarization to help an analyst to quickly get the gist of a document rather than reading the entire document. I use document similarity for the kind of like bottom part of the hourglass, where the analyst has found a document of interest, and then the document similarity analysis can automatically point to other documents that are similar and therefore might also be of interest. Then I've also implemented document clustering, which is really useful for the top of the hourglass, where I really don't know yet what to investigate, but if I cluster my documents according to content and create some themes, it's much easier to pick a subset to start the investigation with. And finally, I did implement a sentiment analysis that is not useful in all domains, but there are a couple of domains where it really can facilitate the analytical process. One example are reviews of products. It's very useful to classify those in kind of like positive and negative reviews, and then relate the sentiment to the entities that are mentioned in those documents to get a quick overview about what is good and what is bad about a specific product. And the Jigsaw system now has a number of views that really provide a lot of different perspectives on those connections between documents and entities and between entities themselves. And the power of the system is that the views can be used in a synchronized way to answer more complex questions rather than using each view individually. And I will give a brief demo to show you how such an analysis will work. In my lab, I really like to use big screens because they are really useful for this type of investigation. The group of Chris North at Virginia Tech has done an interesting study where they looked at the benefit of using large displays for investigative analysis scenarios. And they found out that it's not just about having more pixels, but basically having this big space changes the analytical process because the space becomes part of the analytical process. Analysts can use the space, for example, to arrange a timeline of their insights or a timeline of the data. They can use the space to create clusters within the data that they create and that are not automatically created, but basically that are tailored to what they are doing right now. And therefore, having this big space available really helps kind of like to guide the analytical process. When I was visiting Daniel Keim and Constance, I was really taking advantage of the Powerwall, and I could give a demo that was really showcasing all these views and how they are used in collaboration. But unfortunately, I don't have that here. So you really have to bear with me for a little bit, and there will be some window swapping, and it won't look as elegant as it's on a bigger screen. And I have two examples that I would like to show. In my first scenario, I'm looking at all InfoWiz and VAST conference papers from 1995 to 2011. And I'm using the metadata of the papers, like authors and keywords, as entities, but I also use entities that I automatically extract from the papers based on a dictionary approach, where I just created a dictionary of 80 keywords that are important in the domain. So in this data set, we basically have 578 papers, about 1,100 authors. They are from 2 conferences, 17 years, and we have about 80 concepts, and these are the IEEE or ACM index terms, and those are 1,200 keywords that were specified by the authors. To start, I just open up the list view and put a number of entity types in that list. So I just look at authors, I look at years, and maybe I look at concept terms. And these little bars next to the entity names basically show the co-occurrence. So entities with a large bar occur in many documents. For example, graph is mentioned in over 90 papers, and entities with a short bar occur only in a few documents. Now, I can select entities, and then I will see what's connected to them. So if I select an author, I will see in what year did the author publish, and what other concept and what concepts are connected to those papers. And I can also sort the lists by their frequency. Right now they are sorted alphabetically, but if I sort by frequency, I will see that Stasko has published 19 papers, and so he is the most published author in this set of documents, followed by Daniel Keim, who has published 18 papers. If I now select Daniel Keim and I sort the lists by their strength of connectivity, I will immediately see that insight and text are the most connected concepts to the research of Daniel Keim. And the color coding basically shows the strength of the connectivity. The darker the shade of orange, the stronger the connections is, meaning there are more papers that mention both terms. Do you have a question?
Yeah. So are these connected to analysis done online real time, or do you do this offline? Just showing this, you get this.
No, I do the analysis offline and store it in a database and then just show it. So I now would like to move on and show you how views can be used in collaboration to get more interesting insights. So therefore, I open up the document cluster view, and I just cluster the papers by their similarity of content. And I can just see that there are kind of like different clusters that are related to themes in InfoWiz and VAST. There are some clusters about text visualizations, some clusters about networks, some clusters about graphs, some clusters about animation, and so on. If I now basically put those views side by side, and I select Daniel Keim, the cluster view will show me in which clusters his papers are published. And so I can see that he did a lot of work in text analysis and also in this cluster. The keywords here that summarize the content of the clusters can be either based on the frequency or by more choosing unique words to identify the cluster more uniquely. It's just different parameters in the document summarization clustering. And I can also do it the other way around. So for example, if I select the graph edge algorithm cluster, I can see in the list view that Mantner and Van Herm are authors that have published a lot in this area. So basically using these views in combination just gives me a much deeper insight rather than just using one of the views. And a last example, just looking at the history. If I'm selecting the first 5 years of the conference, I can see that in some clusters, there was a lot of activity. For example, in the querying managed series cluster. And other clusters only had little activity. If I select the last 5 years, I can see that it has changed. So some clusters don't have a lot of papers anymore, whereas other clusters are really becoming a more interesting research area. Now, next I have a second scenario where I have a brief video that demonstrates how to analyze car reviews for the 2009 Hyundai Genesis. And I quickly show that video to really demonstrate you more about the analytical flow that was really difficult to demonstrate in this demo.
This investigation examines 231 consumer reviews of the 2009 Hyundai Genesis from the Edmunds.com website. Jigsaw's list view provides an overview of the reviews showing summary rating, as well as car features, makes, and models mentioned in the text written by each reviewer. The short bar at the front represents the number of documents in which that entity occurs. Sorting lists by frequency thus shows the most commonly noted entities. Overall, ratings for the car appear very good. Moving now to the document grid view, each review is represented by a small rectangle. Colouring and ordering the reviews by their sentiment shows generally positive impressions of the car. Blue represents positive sentiment, and red negative. Alternatively, Jigsaw can order the documents by date. The oldest is in the top left, and the newest in the bottom right. It appears that many of the negative reviews are more recent. We can corroborate the sentiment via cross-view selection. Selecting the reviews in the list view having an overall rating below 8 highlights these reviews in the grid. Some, such as this one, still express positive sentiment in their words. With all the most negative rating reviews selected, we can reorder the car feature entity list by connection strength, thus bringing the highly correlated terms such as seat, tyres, transmission, steering and suspension to the top. Documents in the grid view also can be clustered by their content. Note here that clusters 1 and 8 seem to contain many of the negative sentiment reviews. Let's load each cluster's reviews into a document view. Here's the first. The word cloud at the top highlights key terms throughout this set. Here are the documents from cluster 8. Note the suspension standing out. Returning to the list view, we select all reviews with a perfect overall rating of 10. Sorting the car feature list by connection strength highlights features of the Genesis likely viewed positively by consumers. Sorting the car maker list by frequency, then selecting the 4 top mentioned makes one by one, shows the overall rating of reviews mentioning each of these other car makes. The reviews mentioning BMW seem to provide a slightly lower overall rating. Finally, we load the term ride into the word tree view to see a summary of all the sentence segments following it throughout the reviews. A variety of opinions have been expressed.
So this demo, or this video really shows the analytical flow and that it's much more about having a dialogue about the data through those visualizations rather than just having a simple search. Yeah.
How do you do the sentiment analysis?
I've integrated 2 different approaches. So the link pipe library for text analytics provides a sentiment analysis component, and you can train it, and it's basically trained on product reviews. In this example, I was using my own dictionary-based approach where we defined basically keywords about car reviews in the domain context to identify positive and negative words about the cars, and then we just weighted the number of those words found in the reviews. So what did I learn by building the system and by tightly integrating the computational analyses with those visualizations to really support this interactive process? And I just picked out 4 lessons. There are a few more in the paper that is published. So one thing that became clear immediately is that it's very important to use those computational analysis results across the system and provide them in lots of different contexts with different visualizations, and not just having them as a separate component that is only kind of like working on the side and is not integrated with the views. Because this really facilitates this question answering process where you are either using the visualization or the text analysis to either come up with a better question or to find an answer to your question and then kind of like move on to the next insight. A related point is that it's really important to provide this flexible analysis stream where the output of one view or the insight can be really turned into the input for the next question on the next view. Then going back to the hourglass shape analysis, it's really important to provide support for both ways, to narrow down in your analysis and really find a subset of interest, and then widening up again to find things that are very related to your insight that you just found. And finally, exposing algorithm parameters in an interactive and user-accessible way is really important. And we did that with a couple of different approaches. So for example, for the clustering, I just implemented a basic k-mean clustering approach, and the user can either say that the system should choose the k automatically, or the user can pick it manually if the number of clusters is already known. In this scenario, we directly expose the parameter from the algorithm because it's kind of intuitive. For the text summarization, we went a different approach, and we didn't expose the algorithm parameters, but we rather provided an interface where the user can decide either to summarize the clusters based on only the text or to summarize them based on the uniqueness of terms to clusters. Because we tried at first to expose the algorithm parameters, but the user really couldn't make sense of that, and therefore they didn't use it. But after the change, where we provided an interface that basically abstracts from the underlying algorithm, it was much more user-friendly and much better to use. So what's next? There are still a lot of areas where I'm working on to improve the system. One area is scalability. Right now, the system actually already scales pretty well in some sense. So just last week, we got an interesting email from a collaborator from industry who was using the Jigsaw system for fraud investigation. And he was saying that he was using it on a document collection of 700,000 emails. And he was able to narrow it down to the 40 emails that were really important, and then was able to recover $500,000 in this fraud case. So it does scale already to some degree. However, it doesn't scale very well in terms of the length of text documents. It's really tailored to these short case reports. And especially in the science domain, right now I'm just working with abstracts, but I really would like to move to full text, the full text content of papers. And to do that, I really need to move away from the simple model of entity co-occurrence. If 2 genes co-occur in a paper, it really doesn't mean anything anymore because there's way too much noise. So I now need to find a better model that is semantically typed to represent these connections between different entities, or also between entities and documents. So that's one area I'm working on right now. Another big area is uncertainty. And in unstructured data, especially in text documents, there's different type of uncertainty. One type of uncertainty is really expressed in the documents. If a scientist is saying, I don't have a lot of evidence, but I believe that the experiment indicates this, then the text is explicitly stating that it's not very certain. A second type of uncertainty really comes from the text mining algorithms, because they are not always 100% precise, and they produce false positives. And so I really need to distinguish between these different sources of uncertainty and find good ways to represent them visually to indicate where it comes from and also to indicate how it basically influences the data analysis in terms of those different entities and their connections. Now I would like to move on to the question about how to evaluate those systems that are really tailored towards facilitating sense-making and finding new insight. And it's really, really difficult to evaluate those. And even within the research community, there's not much agreement yet what would be the best way to go. And I've tried a number of different things to evaluate the Jigsaw system. One way is just to have success stories, right? So just give the system to real analysts, to real people, let them work with it on their real data and see if they think it's actually useful. And I will tell a few success stories. But of course, that's not a really scientific measurement about putting a number on the usefulness of the system. A second approach is the contest in the research community. So along with the VAST conference, each year there is a competition where teams can use their systems to analyze a synthetic data set where the ground truth is known, and then the submissions are basically compared to each other, and they are graded based on the insight that the analyst found in relation to the ground truth. And we did participate in a number of those contests. Then a next way to evaluate is to actually have a lab experiment where you have a controlled setting and you compare your system to other approaches, and then you really measure the correctness and the time that the participants of the study basically produce in their data analysis. And finally, there's also longitudinal studies where we can deploy the system and then we follow analysts for a longer period of time to find out what do they struggle with, where does the system help. But I'm not covering the last point in my talk. We did a longitudinal study of the Jigsaw system, but that was basically part of the PhD thesis of Yonor Kang, who was a student of John Stasko and who is now at Google. And if you're interested, I can give you a pointer to that paper. So success stories. We have a couple of collaborators within science and also outside of science that have used the Jigsaw system to really analyze their data, and they have published the results either in a scientific journal or they just basically used it in industry for their own good. We did collaborate with the Aerospace System Design Lab at Georgia Tech, and they basically used the system to analyze or to compare guidelines in the US and Europe for air safety. And they really had some interesting insights that they found using the Jigsaw system, and they published it in the Journal of Aircraft. In a second example, a software engineering lab in New Zealand was using Jigsaw to analyze Java source code, which is really kind of like a stretch of the original domain, but they basically built their custom dictionary using the Java language, and then they used the system to really understand in big projects what are connections between classes, methods, variables, and so on. And they also published an interesting paper about their insights at the SoftBiz conference. I have built a kind of spin-off of the system that is working on the biomedical literature, where you basically do a search on PubMed, you export the search result as an XML, you do some entity identification and import it into the system, and then you use Jigsaw to really better understand what's in these 1,500 papers about the TGF-beta2 gene, rather than just going through the title and abstract list and picking a few that you thought might be interested. And then finally, we have a number of collaborators in the law enforcement and intelligence domain, and some of them have used Jigsaw successfully in their daily work. So we got a nice testimonial from the Washington Joint Analytical Center, where they used Jigsaw to analyze graffiti crime and also trafficking on ferries. And they basically stated that Jigsaw was an invaluable tool when it came to examine these case reports. Without the use of Jigsaw, examining reports would have been tedious and time-consuming, and connections between entities may not have been seen. So they really thought that the Jigsaw system was making a difference in their analytical approach to understand their case reports. And we were really excited about getting such a positive testimonial. Moving on to the second type of evaluation, we did participate in a number of VAS contests. And the original contest in 2007 basically had these two divisions, one for industry and one for academia. And the data set had about 1,500 documents, and the task was to find a hidden thread in these 1,500 documents. And we used a very, very early prototype of Jigsaw, kind of like as a first approach in this contest to figure out what the system does and what is still lacking. And even though it was just a very first prototype, we did win the academic division of the contest. And in the following years, the contest was kind of like changed in challenges that were based on smaller data sets to increase the participation. And we did get awards in 2010 and 2011 for specific aspects of our system. Now, we really wanted to do a more scientific approach to evaluate the usefulness of Jigsaw. And therefore, we did a controlled lab study. And we used 4 different settings with 4 students in each setting as participants. In the first setting, so we generated a small data set with only 50 documents, and the documents were really short, and it was a synthetic data set where we knew the answer, and the question was to find a hidden thread. In the first setting, we just handed out paper copies to those 4 participants. So they only had 50 printouts of the documents, and they had pencil and paper to work on this data. In a second setting, we were just using desktop tools on a Windows system where the students basically could open these electronic version of the documents in a text editor and use a search function to search across the document set. In a third setting, we were using the Jigsaw system, but it was restricted on only one view. We only provided the document view that was showing the document text along with entities that were automatically identified within the document text. So setting 2 and 3 are very similar. The difference is that in setting 3, the students also had the automatically identified entities available. And in the final setting, the students are basically using the complete suite of visualizations within the Jigsaw system. And we did a combination of a quantitative and a qualitative data analysis. So the students had 90 minutes to work on the data, and then they had to write a debriefing with their answers to the questions. And we collected a lot of quantitative data. So for all the settings, we basically scored the answers and compared them with our ground truths. But additionally, we also looked, for example, how many of the documents the students actually read or looked at. And it turns out that in the paper and the desktop setting, the students looked at or read all 50 documents. However, in the Jigsaw setting, some students only looked at a subset of the documents. But they still had an excellent solution to our questions, indicating that the Jigsaw system really helped them to narrow down the documents to read, but they still found the important documents and didn't miss anything important. We also took a number of data points regarding queries that they did and their note-taking behavior. Finally, we analyzed the data according to different strategies. How did the students approach this analytical task? And we came up with 4 different strategies. One we called overview, filter, and detail, where the students first really looked at a couple of documents briefly to get an overview and then narrow down their investigation. A second approach was basically the opposite. Building from detail, a student was just reading 1 or 2 documents, very detailed, and then branching out from what they found in those documents. A third strategy was hitting the keyword. Basically, the students were using search function immediately at the beginning without reading any documents, just having some sort of a guess what might be important and then going from there. And the last strategy, finding a clue and following the trail, was basically a combination of 1 and 2, where they first read a few papers, a few documents, and then followed things that they found in those documents. And interestingly, we found that in the Jigsaw setting, different types of strategies were used, but all resulted to a good score, indicating that the Jigsaw system is kind of flexible and is supporting different way to do this type of analysis. We also looked at more qualitative data. So we recorded all those sessions by video, and we built a logging mechanism within the system to really understand how the views were used and how they really contribute to finding an insight. So these are 8 different participants that were using the Jigsaw system. So each block is 1 participant, each row of pixels is 1 minute, and so each block are 90 minutes. And the color coding indicates which view was used at a specific point. And so these 4 participants only used the document view because they had the restricted system and they had the main view with the overview of the data. In the full Jigsaw setting, it's really interesting to see that participants had kind of like the favorable views. For example, P14, mostly yellow, indicating that he was doing most of the analysis just with the list view. Other participants were kind of like more flexible and were using the views in a synchronized way, how we anticipated it. For example, P13 was using a lot of the document view, but also the graph view, the calendar view, and the timeline view. And so this qualitative analysis combined with the quantitative data that we have really helped us to get a much better understanding of the use of the system and also of the kind of like how it facilitates the sense-making process overall. In the last part of my talk, I would like to present a user-centered design approach that I recently worked on with a collaborator from the University of Michigan, Barbara Morell. And that's in the context of biomedical research. And we really wanted to understand the sense-making process that biomedical researchers apply when they analyze a large data set. And the context of the study was that we observed a biomedical researcher exploring a heart failure problem over 6 months. And the specific question was, what genome-level interactions and events might explain why some heart failure patients did not respond to beta blocker treatment and other patients did respond to beta blocker treatment. And so we collected, again, a lot of data, including 12 hours of audio and video recording of the screens. We collected copies of monthly interviews and her written as well as electronic lab notebooks. And she was using a lot of different tools during that investigation. So she was using Cytoscape and Analyzer, which is a plugin in Cytoscape for network analysis. She was using a lot of different online tools for data analysis and a number of biomedical databases and the biomedical literature. And so after collecting all this data, we collaboratively developed a sense-making model, and from there we derived implications for tool support and design guidelines. Here's just one brief snapshot of our video log, just to give you kind of like a hint on the complexity of this analysis. So on November 15th, 30 minutes into the analysis, the scientist finds a gene pair of interest in String, which is an online tool for these 2 genes. Then she cross-references it with the analyzer network that you can see here in the background, and then calls up related pathway information in the Reactome database. And basically just in the 30 seconds of analysis, she was already using 3 different tools that are really not very connected, and she was synthesizing the information that she was gaining from those tools. And we kind of adopted the Piroli and Card sense-making model from the intelligence domain to showcase how a sense-making model in the biomedical domain for the explorative analysis of molecular interactions might look like. And I'm not going into lots of details. I just want to briefly explain kind of like the high-level view of this model. There's basically 3 different parts. In the first 2 stages at the bottom, the analyst is really working with the primary data, and it's really understanding what are the characteristics of these genes, what are their concepts, what are their functions, how do they relate to each other. In the second part of the analysis, she is moving away from the primary data and is really looking in detail in the biomedical literature. What is already published about those genes? How does that fit into the context of my experiment? What are knowledge gaps? How could I create a hypothesis of the outcome of the experiment, and how could I fill in these knowledge gaps? And in a third stage of the analysis, she's basically putting those insights together to a bigger story and to schematize and to really tell that story to collaborators and to finally publish a paper about it. Of course, this really high-level overview by itself is not yet really useful, and therefore we also really looked into more detail into specific stages of the model. And this is just an example of the analytical process of the stage number 2, including annotations of the tools that were used for the different processes. So for example, for information foraging, she was using really a lot of different tools. For the interactions with collaborators, interestingly, she wasn't using any tools, but only relied on paper printouts. And so taking that into account, now, what is the state of the art in that area? And I found a really interesting quote on a blog by Stephen Previnas, which was in the context of software modeling, but I think it really also applies to this study. And so he was basically saying, think of trying to watch The Empire Strikes Back, but the actors are on your TV, the scenery is on your iPad, and the soundtrack is on an 8-track. And I think this really presents how this analyst was working. She just had to use lots of different tools. Some of them were really, really old, but there was just no better replacement, so she had to use them. Some of them were really new and shiny, and they are really not connected at all. There's just a lot of effort to transfer data from one tool to another tool because there's different formats, they are not compatible, and also there's really no help to support the provenance analysis, to really keep track of where does my insight come from. And so based on that, we developed a couple of guidelines, and I just, again, picked a few more in the paper, how we really could improve tools that address this really complex data analysis. And one really important outcome is that providing provenance in a user-friendly way and indicating the uncertainty of the data and visualization is crucial. Otherwise, the analysis is really not reliable, and the scientist is really struggling in using tools if they don't communicate, like why did they have this finding, where does it come from, and what does it mean? A second outcome is that it's really important to blur the line between input and output and to connect those different tools so that the analyst can have like a smooth transition between questions that are asked across tools and doesn't get stuck in reformatting data. And finally, providing lots of different views on the data along with electronic support for note-taking would be a big improvement, and the recording of the investigation history as well, because those are long-term investigations where the analysis is working for months on a project, and it's difficult to keep track of or to go back in time to figure out where did an insight come from and what else could I investigate. And so we believe if those guidelines would be implemented in those tools, the tools would be much more user-friendly and also much more efficient. If you're interested in learning more about Jigsaw or in getting a copy and using it in your class for teaching or for your own data analysis, we recently just set up the Jigsaw Analytics webpage where you can download the system. There's also a link to the Jigsaw homepage with all the videos, papers, and we also have a lot of data sets online in XML form that you can use for your own analytical purposes. To wrap up, I do have an opening for a postdoc. So anybody who is interested in biological data visualization, please apply. And I would like to acknowledge all my collaborators. So the last part of the talk with the Sensemaking model I did with Barbara Morell from University of Michigan, who is an expert in human-centered analysis. At Georgia Tech, I closely collaborated with Hannah Tipney, who was a postdoc and who now joined industry in the UK. and also with Bill and Kevin, who helped a lot with the integration of the text mining approaches into BioJigsaw. And of course, I would like to thank Larry Hunter, who is my mentor at CU Denver. Back at Georgia Tech during my postdoc, I worked with lots of students on the development, the design, and also the evaluation of the Jigsaw system. Jisheng Liu, who is now a postdoc at Stanford, did a lot of the work to implement the system. Yona Kang, who's now at Google, helped a lot with the evaluation. And there were also a number of graduate and undergraduate students who did implement some of the views. And finally, I would like to thank John Stasker, who was a PI to provide me the opportunity to work on that data. And with that, I'm happy to answer your questions.